Let's um, uh, uh, dear colleagues, let's start our today's talk. Today's speaker is Professor Satoshi Nawata, who is now in Fudan University, and he will tell us about Skein algebras, double affine Hecke algebras, and Brane quantization. Let's welcome.
Okay, thank you very much for invitation, and then I really appreciate the organizers for invitation, the kind invitation, for and providing a chance to talk today. And sorry about last week. I don't know the why, but the connection was bad. Today I'm going to talk about some relation between Skein algebra and also double affine Hecke algebra and Brane quantization. This talk is based on two works. The one is the brilliant colleagues Sergei Gukov, Peter Korotev, Dupay, and Ingmar Sabari. And then, if time permits, my recent work on with my students at Fudan. Feel free to ask me anytime during the talk. Okay, so the problem is we want to consider its quantization on simplex manifold. So there are famous two ways to do the quantization. There are famous two quantization scheme. One is called deformation quantization, and the other is German quantization for simplex manifold. So deformation quantization, you just consider a ring of function of the simplex manifold. I call it M and omega is the simplex manifold. And you consider this ring of function over the simplex manifold. And you just quantize the ring of simplex function by introducing H bar. And the way you quantize is just using the Poisson bracket. Just uplift the Poisson bracket to commutation relation, and then that is somehow somewhat called the quantized deformed algebra A. That is the deformation quantization. It was the famous work by Quantization and so on. It was studied intensively. More historically, the German quantization procedure came earlier. So German quantization is you just consider the simplex manifold M, and you just consider pre-quantum bundle, and whose Turing class is proportional to this simplex form omega, and then this simplex form, and then you just consider some Dolboko homology with value of this pre-quantum bundle with the square root of this canonical bundle over the simplex manifold M, and this will give you some vector space, which is called quantum Hilbert space. And many of you are very, how to say, familiar with Chern-Simons theory and so on. So this quantum Hilbert space plays an important role in how to say, the quantum topology, 3-manifold, Jones polynomial, and so on. So these two quantizations, given these two quantization schemes, we have algebra coming from deformation quantization, and we have a Hilbert space or vector space coming from German quantization. Can we construct representation theory of this algebra A using deformation obtained by deformation quantization on this Hilbert space obtained from German quantization, but using by some simplex geometry? That's a question I want to ask. This question was answered by Google Witten in the mid 2007 or 8. So first we consider the so-called complexification of the simplex manifold, original simplex of M. Complexification is that you have to double the dimension, and you consider the X is the holomorphic symplectic, and also we want to have it affine. For instance, if you consider locally, it look like cotangent bundle of the original symplectic manifold. Then this space is a holomorphic symplectic. Moreover, it's hyperkähler and a affine variety. Okay, affine algebraic variety. So this is the setting you consider, and then we want to consider the so-called A model, or like a Skein category. A model is some physics language for Skein category to describe Skein category. Anyway, so to consider the Skein category of this the complexification, the affine hyperkähler manifold X with particular symplectic form. Okay, and then we want to consider Skein category on this the X, and then usual in Skein category object of the Skein category is the Lagrangian submanifold, and then here so we the original symplectic form M itself is the Lagrangian submanifold with respect to some symplectic form omega X. And then we considered in the object of Skein category is that it endowed with some data. So that is called you consider some vector bundle over the Lagrangian submanifold M, and then you consider flat unitary bundle, unitary connection on this vector bundle. In other words, you consider local system over this Lagrangian submanifold. And then this is the usual object in the Skein category. And then people, anyway, so in physicist language, we call it A-brane, ordinary A-brane, Lagrangian A-brane. However, one can also consider, in physics predicts that there exists big A-brane for the, which is supported on the co-isotropic submanifold inside the X. Co-isotropic submanifold is that they are locally defined by Poisson commuting functions. For instance, you have a bunch of the affine subvarieties. So like F1 is equal to 0, F2 is equal to 0, F3 equal to 0, and so on. They're all Fi and Fj are Poisson commuting like this way. And this will cut out some submanifold inside this affine variety X. That is called the co-isotropic submanifold. And then the number of data, the maximum number of this Poisson commuting function is actually half a dimension of this X. So therefore, in that case, if the number of function which define the submanifold like this way is the maximum half a dimension of that this X, then in that case the submanifold is Lagrangian itself. Lagrangian. On the other hand, the co-isotropic submanifold can be, less number of the function can define the submanifold. So therefore, co-isotropic submanifold can be higher dimensional submanifold than the Lagrangian submanifold. In particular, physicists predict that there exists some distinguished object called canonical co-isotropic submanifold brane, which is sometimes often called A-brane, which is supported on the affine hyperkähler manifold itself. Okay, and you consider some line bundle over it, and the whose curvature is given in like this F, and the F, and then this symplectic form, and corrected by this so-called B field in the physicist language. This we just take H2 of X in R. If you consider this combination, you get the holomorphic symplectic form for this affine hyperkähler manifold, scaled by this H bar, scaled by H bar. And this J, I will explain what's the meaning of J later. This, in any case, this some associated to the complex structure in this hyperkähler manifold. It's a hyperkähler manifold. There is an I and a J and a K. are the symplectic form. Complex structure in the hyperkähler manifold, and this capital omega J is the holomorphic symplectic form with respect to for this complex structure J. So this is the setting we consider to realize to connect deformation quantization and geometric quantization. This is the setting. Any question at this moment? Okay, let me move on. How do you connect the deformation quantization and geometric quantization? So I call it this way. This big A brane is called BCC. So CC means a canonical coisotropic, and B means brane. Essentially, this is the some exotic distinguished object in enlarged category in math language, which has not been defined, but there are a lot physicists predict this should be included in the Sky category, in enlarged version of Sky category. And you can consider the morphism between this single object in Sky category. And in fact, this morphism in physics is just open string between two boundary conditions. So BCC, there's the open string here, and the boundary conditions is given by this BCC boundary condition.
Am I right that branes are usually 5-dimensional?
5-dimensional?
So what are the dimensions of branes? So actually, I think participants of our seminar are not physically oriented.
I understand. So as I mentioned, so the brane is here, is given here. So usually object in is the Lagrangian submanifold. It's supported on Lagrangian submanifold in this affine hyperkähler manifold. Okay. So therefore, so if hyperkähler manifold X is, say, dimension of hyperkähler manifold 4n, this should be 2n dimensional. Okay, 2n dimensional. On the other hand, this BCC is the dimension is the it's just a dimension of BCC. The support of BCC X is 4n itself. So the support of this boundary condition is the entire affine hyperkähler manifold. In my story, so this X is a real dimension of X is, in my story, is 4, always 4. And then real dimension of this Lagrangian is 2. So this is my setting. But in physics, there are lots of brane, but it's just an object in Sky category. In math language, you can consider it as an object in Sky category. In simplex manifold here. In physics, there are many branes, but we just consider some particular physical brane, but which is the object in Sky category. Any question at this moment? Okay. So you can consider morphism in Sky category, which is the usually given by the Floch complex. But in the case of this, using this big brane, distinguished BCC boundary condition, so you can consider the some nice product structure in this morphism space. So you consider the morphism between this BCC is open string between BCC boundary condition, and you bring two strings like this way, and you just join like this way. If you join this one, you get another BCC string. Okay? If you join like this way, this means that the element inside the home BCC, you have an X here. you have a y here, you can define x times y, which is the home BCC. Okay. So in this, so therefore, in this morphism space, you can just consider the product structure in this morphism space. And in fact, if you consider this morphism space, this is actually essentially the local homology of this affine hyperkähler manifold, double cohomology within L. In L, so that with appropriate boundary condition, it's just a double cohomology of X on C. So and then this product structure will give you the a ring of function over this affine hyperkähler manifold X. Okay? So the morphism space is all the ring of function on X, and since we introduced this H bar here, in fact, this morphism space will give you further quantization, deformation quantization of this ring of function on this affine hyperkähler manifold with respect to this holomorphic simplex form J. So in this way, if you consider morphism between BCC and BCC, one can obtain deformation quantization of ring of function over the affine hyperkähler manifold. So you get the algebra A. On the other hand, so I don't need this. Sorry.
What is omega J?
Yes.
What is omega J?
Omega J is a holomorphic simplex form. Holomorphic simplex form which can be obtained from this curvature and the simplex form. I will explain omega J later more explicitly. I will explain this omega J more.
Excuse me, you're talking about quantization. Do you
Yes.
have any categorification here?
Categorification. I can connect to categorification later.
Okay, great.
Yeah. Okay, and then another thing is that you can consider also the morphism between this BCC boundary condition and the usual Lagrangian. So this Lagrangian A-brane or ordinary object in Hecke category between BCC and the ordinary Lagrangian A-brane. And then here, this will give you actually a German quantization. So you just consider this is H double cohomology and the M and L cross square root K, this one. So this is the original German quantization of the simplex manifold M. So you get the Hilbert space. And in fact, if you consider that this is the BCC BM, so sorry, this is BCC BM string and the BCC string, you can have a joining like this way. You get the BCC BM. You get the. So this means that the morphism between BCC BM receive the action of morphism between BCC BCC. Since this home BCC you have an algebra, and the home BCC BM BCC you get a Hilbert space. This is coming from German quantization. And this joining picture of string will give you the action of the algebra on the Hilbert space. Okay, that is exactly what we want from the first slide. So therefore, using this scheme, we can have this deformation quantization and German quantization at both hands, and then its action, it's a representation. And in fact, here this Hilbert space is constructed from this Lagrangian summer for M, so that given the ordinary Lagrangian summer for, you can have the representation, okay, of the algebra A. So there's a one-to-one correspondence between Lagrangian sum manifold in X and the representation of the A. Okay. So therefore, here you have you can connect between geometry and representation. So what I want to talk about today is that so you have a category of Brane, which is some kind of Gaia category of the affine hyperkähler manifold, and its object, usual object, is this Lagrangian Brane, or Lagrangian local system of Lagrangian, and it just mapped to the representation of the deformation quantization of this hyperkähler manifold. So the left-hand side is the geometric category, symplectic geometric category. Right-hand side is representation theory category. And this joining string picture will connect between these two. Okay. And in particular, this Hom/BCC will give you the functor between these two, and the physics predicted that this one will give you equivalence, derived equivalence of the two categories. So therefore, this BCC is called a generating object in this geometric category. Any question at this moment?
Excuse me, I have one small question. Here I'm a little
Yes.
confused. In the second figure, B prime is actually BM, right?
Yeah, BM, sorry, BM.
Thank you.
Yeah. So in particular, if the support of M, so this support of M is a compact, this corresponds to finite dimensional A module. If M is non-compact, it corresponds to infinite dimensional A module. That's a correspondence. Now I want to connect to Skein algebra. Most of the audience are interested in. Many of the audience are interested in. And then, so let us recall what is a Skein algebra Skein module. Skein algebra. So let's consider type A1 Skein module, first module of the oriented three manifold M3. It's just that you consider isotropy class of frame ring in M3, and you impose some Skein relation like this. Okay, so this is the graded some vector space, and you just have you just impose this Skein relation on this frame ring, and that will give you the A1 type the Skein module. And in particular, when you Q parameter is in Skein relation, when you say Q equal to 1, this Skein module will give you this ring of function on the modular space of Lie connection of over the three manifold you consider SL2C. In other words, you get the SL2C character variety on three manifold when you set Q goes to 1 limit. Okay, so. And the Skein algebra is that you consider Skein algebra is associated to Riemann surface C. It's a two-dimensional real manifold, real two-dimensional manifold, oriented cross surface C, and you just thicken it by segment, and then you consider Skein module of this one. Okay, Skein module of this thickened three manifold. Okay, thickened cross surface. It received the algebra structure by just considering stacking of the how to say thickened Riemann surface. So you have a Riemann surface, whatever Riemann surface, you have thickened one, and you have considered Skein module, and you consider another thickened the Riemann surface, and if you just join them together, you get the product structure in between. In this way, one can have given the oriented surface, you can have an algebra structure. And in fact, if you take Q goes to 1 limit of this algebra, this will give you the SL2C character variety, a ring of function over the ring of function over this SL2C character variety over the oriented surface C. In particular, Skein algebra is actually deformation quantization of coordinate ring on the SL2C character variety with particular holomorphic syntactic form. As I mentioned, this is omega J. I mentioned in particular omega J. I will explain. I will construct this explicit example. What is omega J is, but this is exactly the object we consider in here. So this algebra A is obtained by Hom BCC on a affine hyperkähler manifold. This algebra A is exactly we want to it's Skein algebra. We want to consider correspond to Skein algebra in this talk. Any question at this moment? Fine. So now we can see some connection between the Brane quantization and the Skein algebra, because I mean Skein algebra itself is the deformation quantization corner ring of the SL2C character variety, which is affine hyperkähler. And in particular, so this if you have the three manifold with boundary C, this is M3. If you consider this kind of setting, so maybe I should write down like this way. If you can consider this kind of setting, this is C M3. And on C you can associate Skein algebra, and on M3 you can associate the Skein module, and then just pushing the link into the M3 will give you the action of Skein algebra on the Skein module. So this is a very natural action. And in fact, and this is a representation of the Skein algebra. And then so this picture is exactly that fits into the Brane quantization scheme, because I mean this M flat SL2C character variety on C associated C is affine hyperkähler, but on the other hand, SL2C character variety on M3 with boundary of C is that the holomorphic Lagrangian submanifold inside this affine hyperkähler variety. So therefore, one can consider usual Lagrangian manifold. So this can be M, this can be X in the Brane quantization scheme. Okay, and then Hom BCC will give you deformation quantization of this corner ring on this character variety. It will give it's exactly Skein algebra on oriented surface. And then its Skein module is just a morphism between Brane supported on this holomorphic Lagrangian submanifold between so that I call it BH. I mean, it used to be BM. The reason why I call it H is it's coming from Hegard. So because this is Hegard splitting on M3. But anyway, so this will give you representation of this Skein algebra. So you just consider morphism between BCC and then BH. So that will give you Skein module. The reason, and this is the correspondence between the Skein module and then holomorphic Lagrangian inside the hyperkähler manifold, or we consider, I call it the frac X. So that's the connection between Skein module and Brane quantization at this moment. So any question at this moment?
Maybe sorry, maybe I missed. Could you remind me what is the ABA Brane?
Good. Thank you very much. So here, this X is a hyperkähler. So it has the simplex form. No, sorry, complex structure IJK. I will explain how do you obtain this complex structure later. So ABM is ABM is in this complex structure, you can associate small omega I, which is Keller form. So A means Lagrangian, and B means holomorphic. So therefore, so in complex structure J, this the support of this holomorphic Lagrangian is the holomorphic in J, but Lagrangian with respect to I and K. So it's if you restrict omega K on this M flat H, which is M flat M3 SL2C. Okay, SL2C. Then this should be 0. So that means Lagrangian. So this ABA means the IJK. In terms of IJK, it's Lagrangian holomorphic Lagrangian. That's what it means.
Thank you.
Any other questions? Now, I just want to explain what's, so since he asked the question IJK means, what does IJK means? So our Affine hyperkinetic manifold is this SL2C character variety. And in particular, sorry, there's a typo. This is not the full punctured sphere. This is the once punctured torus. CP. So this is typo. Sorry. In this talk, what I want to consider is some SL2C character variety on the once punctured torus CP. And then the fundamental group of this once punctured torus is given by here. M is so once punctured torus look like this way. And then M is just meridian like this M. L is the longitude. And then if you take ML, M inverse L, inverse C is the monodromy around the puncture C, like this. Okay. So this is the fundamental group of the once puncture torus. And if you consider SL2C character variety, or modulus space of Flack function over this SL2C Flack function, you get a hyperkinetic manifold. And in fact, this one can be described by this cubic surface, affine cubic surface. So this one is the X, Y, Z are coordinate in C3, and the affine this equation, cubic equation, cuts out its complex two-dimensional submanifold. That is this SL2C character variety on the once function form. Okay, and then so this it's a hyperkinetic manifold, and then this perspective is coming from complex structure J. So complex structure J means that this complex structure J coming from complex structure coming from SL2C. Moreover, if you want to say X is in fact trace of holonomy of M, and Y is trace of holonomy of L, and Z is the trace of holonomy M times L inverse. So that's the okay. So therefore these variable X, Y, and Z are holomorphic. X, Y, Z in holomorphic in complex structure J. So it's coming from this complex structure. On the other hand, so this complex structure I perspective is coming from this so-called modulus space of parabolic Higgs bundle on the once punctured torus. So Higgs bundle is just a pair of rank 2 holomorphic vector bundle and the Higgs field phi, which takes the coming from here holomorphic section of the once punctured torus. K is the canonical bundle. And you just impose a stability condition called Hitchin equation. So F is equal to phi and phi bar is equal to 0, and dA bar phi to be equal to 0. So that's the stability condition. And in fact, this modular space is diffeomorphic to this space. Okay, and then diffeomorphic. So that is called non-abelian Hodge correspondence. That's called diffeomorphic. And then this everything that complex structure I is coming from this complex structure coming from this Riemann surface which is one function torus. And you have to impose some boundary condition on this puncture torus, on the puncture on the torus. And the boundary condition imposed is as given here. So alpha, A is the connection of this vector bundle, and phi is a Higgs field, and then alpha and beta gamma is actually, it takes the Cartan subalgebra of this SL2C. So they form is inside a Cartan subalgebra of SL2C, SL2 Cartan subalgebra. And in fact, so I didn't explain very carefully in this affine cubic surface, this T is coming from the holonomy around this puncture. So the holonomy around this puncture is trace of the holonomy of C is given by trace of T square T minus 2, 0, 0. So this T parameter is really coming from the holonomy around this one puncture. And in fact, this T parameter is related to alpha and gamma in this ramification of a Higgs bundle. Okay, so here you consider the Z. Sorry, let me take. So Z is the this is a one puncture torus. Z is a local coordinate here, and the theta is the angle around here. So Z is actually R times e to the I theta. So the theta here is an angle coordinate, and Z is a holomorphic coordinate around this Riemann surface. Okay. So that's the our X. Affine hyperkinetic. Okay. Any question at this moment? Fine. If not, let me move on. Okay, so I haven't explained the connection to double affine algebra, and now our target is just do the deformation quantization coordinate ring of this this space. And this one is, as I mentioned, is related to the Skein algebra, because I mean, given the surface coordinate deformation quantization coordinate ring will give you Skein algebra on C. Okay, and so therefore, if you consider this space as an X, naturally we get some kind of Skein algebra. But there is another perspective of deformation quantization of this space or coordinate ring of this space is coming from double affine Hecke algebra. This is given by Jelinek. So to introduce double affine Hecke algebra, it's most illuminating to consider so-called orbifold fundamental group on the one function torus mod Z2. It's a closed. So if you consider this orbifold fundamental group of this this space, you have this generator T generator. Since this is a fundamental how to say universal covering of torus, and there is a puncture here. You have a puncture here. So this is a P, your P, and then the fundamental. This is a fundamental domain of torus. And then you just Z action is you just identify opposite point between this dotted line. So you just Z action is given by the X goes to 1 over. Sorry. Anyway, so the Z2 action. So this Z2 action is all before Z2 action is just you just identify the opposite point with respect to this function. Okay. Then in that case, this fundamental group is generated by T and X and Y. So these are the generator of fundamental group. And then there is a relation between these generator. For instance, you have a T, sorry. So you have a once you have a T action, the arrow if the x is up becomes reversed. So Tx Tx. You have a Tx Tx is equal to 1. That will give you this relation. Okay. And also T y inverse T y inverse T y inverse T y inverse is equal to 1. That will give you this relation. And another thing is T square x y x inverse y inverse. That is giving this relation. Okay, is equal to trivial. That is a OV4 fundamental group you consider. Double affine Hecke algebra is in fact the so this is called double affine Brane group. In fact, double affine Hecke algebra is just you just add the Hecke relation into this group algebra of this OV4 fundamental group. In addition to that, you deform this relation by introducing Q inverse. Okay, so you just consider group algebra of this one, and you add the Hecke relation for this capital T, and then you introduce small different quantization parameter Q. So that is called double affine Hecke algebra. So this is called Hecke algebra, which is quantization of the usual Z2. So the Y group is given Y group of SL2. SL2 is Z2, which is T squared is equal to 1.
Excuse me,
You
you are talking about braids. Can we get invariance of knots here?
The short answer is so from here, so this is called affine braid, double affine braid group it's called. But from here, you cannot simply get the knot invariance. But from Daha, one can obtain at least torus knot invariance.
So what do you mean by torus knots?
So as you, so I will explain later in the next slides. So this Daha receive SL to the action, PSL to the action. And because I mean it's coming from these two torus. You have a two torus, so therefore you have a SL to the action. But using this SL to the action, one can obtain the torus knot invariance by via Rosson-Jones way, and that will give you the categorification.
Torus knots. So torus knots. Do I mean thickened torus or full torus or what?
I mean just T comma MN, this kind of torus knot.
Okay. So you mean a very, very I thought all knots inside the torus, and now you are meaning a very, very special case of usual knots in S3 R3.
Yeah. It's a very
I
very
thought we're talking about knots in the thickened torus.
Yes, so the torus knot invariance can be obtained by via Rosson-Jones, and that will give you categorization of Humphrey PT polynomial. That using Daha. That is done by
not for all knots, but for very specific knots, right?
the torus knot. Only torus knot.
Yes. Only a very special.
Yeah, very special one.
Okay.
That can be obtained. That was done by Aganagi Shakirov. I don't remember, 2012, I forgot, 11, I forgot. And Cherenik also wrote a paper. By using that. Anyway, let me move on. So that our target is the not invariance, but this quantization of this character variety. To connect the quantization of this character variety, you just do the sum subalgebra of this double Hecke algebra. I have to mention one thing. So Hecke algebra is deformation of this Wall group by introducing this deformation parameter T. And then the affine means that you impose this X variable and you impose this kind of relation. That is called affinization. Since you have an X and a Y, both two variables, that's why it's called double affine. And you have a Hecke algebra, so that's why it's called double affine Hecke algebra. That's the origin of the name. And you can easily see, so here is the small t, and we already see the small t in this character variety. And I will connect this t to this t. And there's a Q here, and Q, we already see many times this whatever Skein algebra, deformation quantization, and so on. So that's the relation between deformation parameter among them. Okay. To connect the deformation quantization story, so we just consider subalgebra of this double affine Hecke algebra. So H double dot is this double affine Hecke algebra, and E is idempotent inside of this double Hecke algebra. E squared is equal to E. This is idempotent, and you just consider idempotent projection of this double Hecke algebra. That is called Spraker subalgebra of double affine Hecke algebra. And then these are generated by X, Y, Z, which is given by in this way. Capital X, Y, we already see here, X and Y here. And idempotent E is defined by capital T and small t. So, and the X, Y, Z, which is already you already encountered for the coordinate of character variety. And then this Spraker-Daha is actually relation between X, Y, Z is given by here. Here, Q commutator is given by Q to the 1/2 xy minus Q to the minus 1/2 yx. That's a Q commutator in given here. Okay, it's given by like this way. So everything cyclic, and then the last equation is something kind of Casimir element, because I mean the left hand side is given by generator of X, Y, Z of the Spraker-Daha. But the right-hand side is everything's deformation parameter, which commute with any element in this algebra. Fine. And if you look at this algebra relation very carefully and send Q goes to one limit, this Casimir element is exactly the one we saw in here. This is the character variety on the one function torus. This is the character variety on one function torus. Okay. And then here X and Y, and when you set Q go to one limit, of course, right hand side is equal to 0. So therefore, everything becomes commutative. So therefore, the Q goes to one limit of the Spraker-Daha is in fact the ring of corner ring of the affine hyperkähler variety or character variety of the one function torus. And this SH itself is the deformation quantization of this character variety with respect to capital omega J. So this is another connection of the deformation quantization of the character variety coming from the double Hecke algebra. Okay. Any question at this moment? Okay. Since so Daha is coming from torus, so therefore we receive the SL2Z automorphism. So here is the capital T usual in the PSL2Z, and this is just some, I already forgot, ST inverse or something like that. Anyway, so this the PSL2Z is generated by these metrics, and then this sigma is usually called S element, and this tau whatever minus corresponds capital T in PSL2Z. And they act as the generator like this way and generator XYZ. So we already knew that XYZ are a generator of spherical Daha, and they are mapped to like this way. Okay. Yeah, as you can easily see, so in the S transformation, as you know, so this X really come from meridian and Y come from longitude. So S transformation swap between these two. That's it. It's a natural way of constructing S transformation of the torus, and that exactly happened here. So the X and the Y are swapped by S transformation. And so the other thing is that you have this sign change action on the generator. X is mapped to minus X, Z is mapped to minus C. This is which is Z2. Another sign group flip element is Y goes to minus Y, Z goes to minus C. That is another Z2. Okay, those are symmetry of this algebra. Any question at this moment? So now, my goal is to consider X is the this SS2C character variety on a one-functional torus, and we want to consider the Skein algebra or a spherical Daha. Skein algebra, spherical Daha, which is deformation quantization of this coordinate ring of this character variety. Okay, by using Brane quantization. So they consider Lagrangian Brane on this character variety, and then it's corresponding to representation of this Skein algebra or spherical Daha. Any question at this moment? So from now on, I just want to connect between Lagrangian inside of this character variety, and then representation of the Skein algebra. Any question at this moment? That's the goal of my talk. Fine. So now let's consider the most famous representation for this spherical Daha or the Skein algebra. The reason why Chernock introduced for double affine Hecke algebra is to study Maclaurin polynomial. And then this spherical Daha has so-called polynomial representation, which is the action on the ring of symmetric function on symmetric function with one variable. Z2 is acts on X goes to X inverse. Yeah, like this way. And then CQT is the ring of function, ring of rational function with variable Q and T. It is generator of the spherical Daha or Skein algebra is XYZ, as I mentioned many times, is mapped like this way. Small x is mapped to capital X plus X inverse. Small y is mapped to some difference operator, like this way. So this how to say, Kali pi acts on function X. Kali pi acts on X is Q shift operator, like this way. So therefore, if you have n power, you have like this way. Okay, and this is actually this difference operator. So this difference operator is called Maclaurin difference operator, and in fact, this ring of function, same function, is spanned by this Maclaurin polynomial. Like it's generally expressed by this hypergeometric series, Q hypergeometric, basic hypergeometric series. And for instance, so J is the number of boxes of it's SL2C. So its representation is always one row. So the number of boxes is J. Okay. And then for instance, P0 is 1, and P1 is X plus X inverse, and P2 is some X squared plus some rational function, and X minus 2, and so on. And so on. So those are explicitly you can write down the Maclaurin polynomial with respect to variable X and then Q and T. And in particular, this Maclaurin difference operator acts on diagonally on this Maclaurin polynomial, and whose eigenvalue is given by here. So that this Maclaurin polynomial is eigenfunction of this difference operator. And this is the infinite dimensional representation because I mean J runs from 0 to infinity. So that's the most famous representation of this algebra. Now we can connect the relation to Skein module. Skein module, in fact, when you set this parameter t, those t many times it appear in the Daha, this parameter t, the parameter t. When you set t equal to q, this is exactly the Skein algebra of the torus, on the torus. Okay. And then, as I mentioned, Skein algebra can act on the three manifold with boundary of the torus T, two torus, which is the simplest one is the solid torus, which is the complement of unknot. And this you can consider Skein module of this solid torus, which receive the action of the Skein algebra. And it's in fact is the infinite dimensional representation, and then it's it's generated by it's called Chebyshev polynomial of second kind, which can be obtained by this recursively by this relation. And in fact, this Macdonald polynomial T equals Q specialization of this Macdonald polynomial will give you this Chebyshev polynomial. So therefore, in fact, this polynomial representation at the t is equal to q is exactly give you this Skein module. The representation of Skein algebra related to the Skein module of the solid torus. So what's happening? Really happening is that you have a solid torus, and you have a Wilson loop. Okay, so the loop are not inside, and it's colored by J. J is of course this the number of boxes, and then this one is represented by this Chebyshev polynomial of second kind as a Skein module. Okay, any question at this moment? Fine. If not, let me move on. Here, one can
excuse
just
me.
yes.
I'm sorry. Of the Daha was defined from punctured torus, right?
Yes.
And when we restrict to spherical Daha,
Yeah.
we change it to just torus in some sense.
No, spherical still keep this t parameter. Still keep t parameter. So, but still have a puncture. But to go to Skein algebra, Skein algebra, we need to set the t equal to q. From puncture to no puncture torus, you need to set t equal to q. So that's the meaning.
Okay.
Yeah.
Thank you.
Yeah. And in fact, there's a way to define Skein. Even with t, it's called, I forgot the name. Sorry, decorated Skein algebra or something like that. You can have a Riemann surface. It's oriented surface. You can have a puncture to define the Skein algebra. There's a way to do that. That will exactly give you this relation. Anyway. Fine. So, and we already knew that this Skein module is exactly the holomorphic Lagrangian defined by this solid torus, the characterability of solid torus, and the inside of this characterability of torus. And this is exactly what's really happening for Daha itself. So polynomial representation is in fact given by like a Macdonald difference of product of Macdonald polynomial. You get this one. Okay, and then once you take classical limit, q goes to one limit, you have a t plus t inverse. So y is equal to t plus t inverse. So this is the equation for this polynomial representation that would define holomorphic Lagrangian inside this character variety. Character variety equation is given here. So once you set the y is equal to t plus t inverse, then the rest of the equation is follows. So rest of the equation is z is equal to t inverse x. This one will define the holomorphic this holomorphic Lagrangian submanifold inside X. Holomorphic Lagrangian submanifold with respect to omega j. Yes. And then once you set the t equal to 1 limit, you get the y equal to 2 and z equal to x. This is exactly the Skein module solid torus, which cuts out the character variety of torus, SL2C character variety on torus. And that it can be understood that the A polynomial R naught, which is y equal to y, and the capital Y equal to y. And the small y is capital Y plus y inverse. Okay. Like this thing. Yes. And PSL2C, the action acts on this holomorphic Lagrangian, and that will just give you like this. But using this PSL2Z action, one can obtain these, as I mentioned, the Vasily asked a question whether we can obtain the knot invariance for torus knot. So given a torus, there's a PSL2Z action, PSL2Z action. From there, from R knot to there is some whatever torus knot one can obtain TMN. Using this PSL2Z action, one can construct the torus knot invariance. That can be done. But in this case, it's just a SL2 invariance, because I mean everything is A1 type in this talk so far. So it's just some deformation of Jones polynomial with T. That is actually related to coponal homology of SL2. Any question at this moment? Okay. So that's the infinite dimensional representation. And then if you consider this polynomial representation very carefully, one can construct so-called raising and lowering operator. So this P is Maclaurin polynomial. This subscript is the number of the boxes, like this way, for Maclaurin polynomial. And the raising operator is defined by X and Z in the Sprague-Daha. Lowering also operator X and Z, but with different coefficient. And if you define like this way, and under polynomial representation, this Pj is mapped to Pj plus 1. Action of this rating operator will increase the number of boxes by plus 1. On the other hand, this action of L under polynomial representation decrease the number of the box by 1. Okay, up to some coefficient. And in fact, this in the case of raising operator, so this prefactor cancel with denominator of this Maclaurin polynomial. So therefore, this raising operator never become null or banish. It doesn't banish. On the other hand, lowering operator, when this red factor vanishes, this becomes null vector, so it becomes 0. Lowering operator becomes 0. And if you look at this, this red factor becomes 0 is exactly this condition. Q to the 2n is equal to 1. This part is becomes 0. T squared is equal to minus Q to the k. This part is 0. T squared is equal to this number. This part is also 0. And then this has to be odd number because to avoid the denominator to be 0. So under these three conditions, this lowering operator becomes 0. So therefore, if you consider this polynomial representation, polynomial representation is the CQT x plus minus ring of functions Z2. It's generated by ideal. So ideal generated by this Pn. This will give you, so you just quotient out finite dimensional representation of spherical Daha. So what's really happening is that when this part becomes 0, you throw away the right infinite dimensional right ideal given by here. You consider the representation given here in this one, this one. This is a finite dimensional representation, finite dimensional module. Okay, of spherical Daha. And the question is, what is the corresponding Lagrangian submanifold in this SF2C character variety? As I mentioned, given the finite dimensional representation, corresponding A-brane, Lagrangian submanifold should be compact. Okay? And to find a compact Lagrangian submanifold, it's eliminating. It's helpful to consider the Hitching vibration. Hitching vibration is the coming from complex I, which map from the modulus Higgs bundle to the trace of phi squared, just invariant of Higgs field. And this is the completely integral system in the sense of Liouville-Arnold. So therefore, so this MH is the Higgs modulus is the Higgs bundle, and to the this BH that it's called Hitching base, and it's affine. It's actually topologically it's just a C. Topological C. It's a completely integrable system. So therefore, if you just consider pre-image of this Hitching vibration, it's just it becomes just torus. It becomes torus generically. It's so that's why this will give you elliptic vibration. However, there's something special going on at the middle fiber in the origin of the Hitching base. There is a singular fiber appear here, and it is exactly look like this way. So there is a 5 copy of S2 or CP1, and join like necklace, like a affine default quiver, like this way. Affine defaulting diagram. Sorry, affine defaulting diagram. And it's called a Kodaira classification. It's called I0 star. It's completely integrable system in that all those like a fiber, it is a component of fiber of the Hitching vibration are all Lagrangian with respect to J and K. Sorry, there's something strange going on. Sorry. So all these fiber are Lagrangian with respect to J and K. On the other hand, it's holomorphic in I because I mean we take complex section I before. Okay. But if you choose some simplex form of X, so we consider simplex manifold X and omega X, and this omega X to be omega K. This is these compact irreducible component are perfect Lagrangian with respect to simplex form here. And in fact, one can compute the dimension of the compare with dimension module, and this the dimension of the spectral space, which is the constructed by geometric quantization. Geometric quantization, one can just compute the holomorphic section of the some bundle on Lagrangian manifold. One can compute by using Hirschsprung-Riemann log, and one can compare with this geometric quantization Hilbert space with the finite dimensional module coming from this polynomial representation with this shortening condition. And in fact, there is a one-to-one correspondence between the compact Lagrangian submanifold and the finite dimensional module. And in fact, this the torus, the Lagrangian submanifold according to the generic fiber of the Hitching vibration torus, that is corresponding to the finite dimensional representation coming from here. This the shortening condition. Shortening condition. That is the, I call it this finite dimensional module, or FM. On the other hand, so this is the middle guy is called Banji, Ban SU2. So this is, if you study Chern-Simons theory, the most favorite one. This will give you the Hilbert space of Chern-Simons theory. So this is the modular space of SU2 flat connection. SU2 flat connection. So this is Lagrangian inside the SL2C flat connection. Flat connection. And this module is the corresponding to the second shortening condition we consider. And as you can see, this K is related to Chern-Simons level K. So also the Lagrangian brane corresponding to this CP1 also corresponding to the third shortening condition coming from the polynomial representation. So therefore, there is a one-to-one match between Lagrangian submanifold inside this character variety and then finite dimensional module coming from in this record. There's a one-to-one correspondence between Lagrangian submanifold in here and then representation of Srekada. So it's a one. So this is a claim is that the compact Lagrangian A-brane corresponding finite dimensional SH module. Any question at this moment? There are many things, interesting things going on here. For instance, so this is two torus, and you can have a holonomy around this non-trivial cycle fundamentals. So since A-brane or like object in sky category always carry local system, so it just always carry this flat connection. So those are parametered by X and Y. And this parameter X and Y on the symplectic geometry side, Lagrangian brane side, is really can be seen at the even Srekadaha side. You can see this kind of like a deformation of the deformation parameter representation in the representation theory side. And furthermore, so this Hitching vibration I draw here is particular case of the Hitching vibration. So as I mentioned, you have a one-functional torus to define the parabolic bundle. You need to impose boundary condition on the in the Higgs bundle on the puncture. And the A is alpha d theta, and the Higgs field take beta plus I gamma dz over z. That's the boundary condition we consider. And then for this configuration to hold, we have to set the beta and the gamma to be 0. On the other hand, I turn on alpha parameter. But if you turn on beta and gamma, this Hitching vibration completely become different. So this this kind of affine default linking down disappear from the Hitching vibration, and instead you have this kind of like a singular fiber will show up. It just it's almost like a pinching two how to say meridian on this generic fiber to get this one. Okay. Yes, and then we can see the Lagrangian submanifold. So these irreducible component also corresponding to Lagrangian submanifold. One can find the corresponding Srekadaha module corresponding to this U1 and U2. And there's a corresponding module. And furthermore, you have a short exact sequence like this way, because I mean, if you combine them together, it looks like a generic fiber, right? So that generic fiber is really corresponding to another module. Therefore, if you just this A-brane is degenerate to here, you can have this bound state of the two A-brane. So therefore, this general picture is corresponding to representation of shorter exact sequence of representations of the spherical Daha. So that exactly match with the geometry side and representation theory side predicted by Brane quantization. Any question at this moment? Okay, so the furthermore, the interesting thing going on. So as I mentioned, so the spherical Daha receive PSA to the action, and then so it's a deformation quantization corner ring of a once functional torus, and the once functional torus also receive PSA to the action. So it's very natural to think which representation of the spherical Daha receive this PSA to the action as automorphism. It turns out that geometrically, if you look at this configuration, geometrically, you can easily see that you can easily guess that it's coming from the torus. So if you have a torus, okay, sorry, maybe it's better to mention torus. Mod Z2 is many people know it's just a pillowcase with four puncture. And then it's a pillowcase. And then if you put some T parameter or alpha, beta, gamma, or this is the complex section J perspective, this is complex I perspective. If you put this holonomy or monodromy parameter, these 4 points become smooth, and then there is a 4S2 will show up. That's exactly what's really happening. And then SA2Z action is really like a T transformation is really like it just do the shift T transformation. S action just swap meridian and longitude. This is exactly happen in the geometrically. So T transformation swap these two S2. S transformation swap these two S2. Okay, so therefore, but under PSA2Z, these three S2 are somehow exchanged. On the other hand, as a set, this one is the invariant as a set in the under PSA2Z, and this one is also invariant under PSA2Z. The question is, what kind of the PSA2Z action acting on this spherical Daha module, okay, corresponding to this CP1? It turns out that this PSA2Z action, okay, let's do the first one, the middle one. This one, as I mentioned, this is coming from Banji or SU2 black connection. Usual Witten Chern-Simons theory story. So therefore, this guy really corresponding to affine SL2 level K representation. This one is actually a modular tensor category. So therefore, it contains the S and T matrix, and this S and T matrix exactly corresponding to PSA to the action. So as you know, if you consider the torus, then this one is you can have an unknot here, and this will receive a PSA to the action in Chern-Simons theory. This Chern-Simons with level K. So that PSA2Z action exactly coincide with this middle guy. A little bit exotic thing is that the PSA2Z action on this one, that is corresponding to the so-called bilateral minimum model. This bilateral minimum model is also the modular tensor category. It has a finite dimensional S and T matrix, PSA2Z matrix. So that is exactly coincided the PSA2Z action acting on this finite dimensional module corresponding to this CP1. And then one can generalize to higher rank. Of course, the middle guy corresponds to SUN version of the Chern-Simons. So SUN affine algebra with level K. And then this guy will become modular tensor category coming from WN minimum model and so on. So therefore, so if you take this modular tensor category, a Grothendieck ring, sorry, not ring. I think it's okay to be ring, but I cannot see the ring structure in this one. So it's if you consider the Grothendieck group of this modular tensor category, that is exactly corresponding to spherical Daha module corresponding to this part and this part. And in fact, if you go to the higher rank version of this one, this is actually so-called bottom row of the Humphrey-Petit homology, triple graded homology of the Kolmogorov-Rosansky of the torus knot. So therefore, so you have like a three completely different vector space are connected by geometry. One is coming from torus knot, the other comes from spherical Daha, the other coming from WN module, minimum model modular tensor category. And the more generalizations, so this part of the connection is already given by Gorski, Oblonkov. Who else? Sorry, Rasmussen and Schende. And this part is much coming from physics, And this part of correspondence is generated by people in Tsinghua. Any question at this moment? Okay, this is kind of one kind of categorization. This is because this is a Humphrey-Petit homology, not just a Humphrey-Petit polynomial. And this is also modular tensor categories categorifications of PSO to the action can be understood as. Any question at this moment? If not, I will bit more talk about the Skein module of three manifold. So there's a remarkable relation between three manifold of the Skein module of three manifold, and somehow it's kind of a categorification of Skein module, which we nowadays both physicists and mathematicians are seeking as a complex version of law homology, instanton-like law homology. If you consider a TKFT, Buffer-Witten, or Marcus or Kapustin-Witten TKFT, everything comes from, it's called, anyway, so if you, for the n equal to 4 super MLs, if you're not familiar with the, physics, it's totally fine to ignore this statement. But Buffer-Witten TKFT and Marcus Kapustin-Witten TKFT, BPS equations known, which can be mathematically rigorously defined. But it's just giving 4-dimensional TKFT. But if you consider the R cross M3 is a 4-dimensional manifold, the BPS equation is actually a complex flat connection, GC connection on 3 manifold. Okay. Usually, this the modular space of this complex flat connection on 3 manifold is non-compact. And also there exists a reducible connection, so on. So highly infinite dimensional. So therefore the Hilbert space of this TKFT is expected to be infinite dimensional. So it's a conjecture coming from physics, it's infinite dimensional. So it's very difficult to formulate as a TKFT, in fact. But surprisingly, so this infinite dimension is graded. So Z graded in general. Some nice setting of M3, it can be much more grade. You can have more gradings. For instance, S1 cross Riemann surface and so on. Such a simple 3-manifold case, you can have more grading. But in any case, each grading, it can be finite dimensional. So this Hilbert space. That's an important thing. So this Hilbert space is the infinite dimensional for this TKFT, but it's a graded vector space, and each grading is a finite dimensional, and then so that's one story. The other story is a three manifold Skein module, and as I mentioned, so it can be understood the set of the formal linear combinational line operating complex Chern-Simons theory.
Excuse
Yes,
me,
go
I
ahead.
read some papers by Gukov about the super polynomial which generalizes both Khovanov and Floer. And so is it proved that we can get Higger-Floer homology, or is it still a conjecture? So there are lots of papers where we have lots of gradings, and it is expected
Yes.
that. Is it proved?
I don't think it's proved, but this Hero space is different from Khovanov-Rozansky homology. It's a different Hero space. Usually, the super polynomial and so on you mentioned is the finite dimensional we consider because I mean it's a categorification on Humphrey PT of knot. And if you do the appropriately normalized version of Humphrey PT, it's just still polynomial. It's not a Roland polynomial. It's a finite dimensional one. And then it's a finite dimensional vector space, and there are lots of grading. Okay, triple graded or quadruple grading. And if you take some differential, one can obtain the Higger-Floer homology. Which is
no. Well, is it a conjecture or is it proved?
It's conjecture.
Okay. Now, what about differentials? So differentials in Khovanov are purely combinatorial. Differentials in Higger-Floer are topology.
Yeah, some cases are proven by Rasmussen. This is some differentials are constructed by Rasmussen. In mathematically.
Okay, and one more question. So you are talking about manifolds. So is there any approach to get invariance of manifolds? Because Khovanov, Humphrey, it works for knots only. It doesn't work for manifolds in full generality.
Okay, that is the recently there's a Google talk by Google Putrov Buffer, Google Putrov Pay Buffer. There's the proposal from physics that you can just have some kind of Q series for three manifold, cross three manifold without knot, which.
So is it again? Is it proved? Is there any?
No, it's nothing proved. Some cases I heard some kind of like within the separate conjecture, some kind of modularity and so on are proven by some very simple three manifold, like a plumbing, like a three manifold and so on, but mostly open.
Okay.
Okay, but your question is different from the what I'm talking about now. It's different from the because I mean the organizer asked about Skein module or Skein algebra, so it's a slightly different topic. I mean, if you want to talk about this kind of like a super polynomial or whatever, the Q series of three manifold invariants or complex Chern-Simons invariants on three manifold, I can give another talk.
Okay, it would be great. Yes,
Okay.
it would be great. So I hope Son John can contact you. Son John, are you here?
Yes.
Yes. So Son John, let's fix some further talk, if possible.
Okay. That's also I can do.
Okay.
Yeah. So because I mean this one I was asked to talk about Skein module, so that's why yeah. So now so what we are trying to connect, so complex version of law homology, then basically, but here of law homology is not complex version. It's just the usual compact version of the gauge group, SUN or something like that, SU2 and so on. SU2, this compact version of the Higgs law homology, but here it's a complexified version of gauge group I'm considering. So that's different from the usual Higgs law homology, which is rigorously defined, but this one is not defined yet. There are many attempts by mathematicians and so on. This whatever version, I forgot the Upside and the Manoleska and so on. But this one proper definition is not known yet. But some version of the this one is already given even mathematician. And I try to connect with the Skein module of three manifold. Basically, Skein module of the three manifold is just a formal linear combination line operator in complex Chern-Simons theory, modular up to this Skein module, Skein relation. And then there's a remarkable fact that this for cross three manifold, Skein module is finite dimensional. So the Skein module we consider so far is a solid torus, the simplest one we consider. This one is infinite dimensional because I mean it's generated by Chebyshev's polynomial, as I mentioned before, but it's not closed. Okay, it's just with boundary. But if you consider the cross three manifold, it's a finite dimensional. That is like a few years ago. There is a technique, sophisticated technique used by Cunningham, Jordan, and Safrano. It's called Witten conjecture and so on, but no longer it's conjecture. Anyway, so that this complex, so the physics predicts the somehow relation between complex homology and the Skein module. One is the infinite dimension, the other is finite dimensional, as follows. If you consider the 0th degree, so it's, as I mentioned, it's a degraded, and if you consider 0th degree of this complex law homology, it is expected to be related to the Skein. Sorry. So here I should mention this one. This one is the Skein of the M3G. So it is isomorphic to the Skein module of three manifold. As I mentioned, the Skein module is the some line operator inside the three manifold, and then this you can have a Higgs decomposition of three manifold. You can have a Higgs decomposition of three manifold, and each piece of the Higgs decomposition. So one piece of Higgs decomposition will provide some ABA brane inside a character variety of C. That's the picture I told you. But if you consider the cross three manifold, you have to join them two pieces together by Higgs by surgery. So that is called Higgs splitting. And that is actually, so you have a two piece of the three manifold with boundary C will give you the two holomorphic Lagrangian submanifold inside a character variety. And in fact, you consider this intersection between these two holomorphic Lagrangian submanifold in this character variety, that is expected to give you Skein module of three manifold. Okay? And if you do the bunch of the map between this intersection between this holomorphic Lagrangian, and that is actually related to complexified version of the three manifold. The law homology, complexified version of law homology of 0th degree. And so therefore, in physics predicts that the Skein module of three manifold, which is finite dimensional, is expected to be a 0th degree of the complex version of Floch homology. That's the relation between the Floch homology, complex version of Floch homology, and the Skein module 3 manifold. Moreover, there is something remarkable prediction coming from this work by group of Buffer, saying that there is some version of the SL2Z action is expected on the Skein module. It's not the usual SL2Z like a module tensor category, like a semi-simple module tensor category. It's kind of it's a non-semi-simple module tensor category you need to consider, and you have to consider some semi-simplification. You have to get rid of like some unnecessary object to make it finite dimensional, and then somehow so physics more bold conjecture is that this three-manifold Skein module is receive the SL2Z or PSL2Z action. That is a speculation from physics, and then so that is a relation prediction coming from physics to the Skein module 3 manifold. Okay, I think I'm running out of time, so I should stop here, and then I'm open to I wait for the question from the audience. Thank you very much.
Okay, thank you very much. Are there some questions or comments? Yeah, I think already many questions are suddenly given from Professor Mantrov. So actually already past time. So let us
Okay.
finish the talk. Thank you very much for interesting talk.
Okay,
And I will
thank you very
contact
much.
you. Yeah, again.
Okay.
Yeah, for your further
Okay.
talk. Thank you.
Okay. Thank you very much. So yeah, if you want to talk about super polynomial and so on, I think I need to prepare another slide. So
Yeah.
so I think we just please contact me via another yeah.
Thank you very much.
Okay, thank you very much. Okay.